Hello, so welcome. We're going to continue talking about the periodic table. Specifically in this video, we're going to talk about periodic trends. When it comes to reading the periodic table, to fully understand how the elements are going to react, you need to be able to properly read the periodic table, which I've completely said in class and in multiple videos because it's very, very important, especially if you want to become a chemist or a physicist. But in order to do that, we need to understand what's called periodic law and identify certain periodic trends. Periodic law states that when elements are arranged in an order of increasing atomic number, there will be a repeating nature of elements with chemical and physical properties, which is what Moseley and Mendeleev proved with their iterations of the periodic table. So that's what's called periodic law. Based off the periodic law, scientists have been able to identify what's called periodic trends. We're going to identify and explore four main ones. The first one is the atomic radius. The next one is ionization energy. And the next one after that is electronegativity, and the next one after that is electron affinity. Okay, so we'll dive into atomic radius. If you have your periodic tables, feel free to get those out at this point. That way you can make some notes in regards to these trends that we can refer to them later on. Otherwise, feel free to take notes as best you can as we go along. But atomic radius is the distance from the nucleus to the outermost electron orbit. So if we go to the Bohr model is kind of in the circular form. So if I go from one end of the circle to the other, it's the diameter. But the radius of a circle is from the center point to one end of the circle. So that center point in this case is the nucleus of the atom, and then the end point is to where that outermost electron or that outermost principal energy level is. So that's what that's identifying. So as the number of subatomic particles, protons, neutrons, and electrons increase, those subatomic particles have to spread out to get rid of this electrical imbalance, and it's primarily due to the electrons, because too many electrons close to each other causes them to repel each other because of the same charge. So they have to spread out, which causes that atomic radius to increase in itself. But based off of that, we can take the atomic radius and say it increases in the following way when reading the periodic table. If you read atomic radius increases as you go from right to left on the periodic table. Okay, and then it increases as you go from the top to the bottom. So it kind of makes sense. As you increase the atomic number, you need to increase the number of electrons needed to neutralize that atom, which means the more electrons you have, the more spread out they have to be, which means the atomic radius has to increase. The biggest atom is francium. It's rarely found. It's not found in its pure form whatsoever. It's very hard to find francium at all because it's so reactive. And the reason why is because it's so big. It has so many electrons it wants to give to not be unstable anymore that it's very highly, highly explosive. So I think there's less than a gram that can be synthesized at one time on Earth of francium. But even at that, I mean, it's enough to, like a grenade. It can go off like a grenade. Ionization energy. Ionization energy is the amount of energy to remove an electron from a particular energy level in an atom. Or, in other words, it's the energy it takes to create an ion of a particular charge. That's the reason why it's called ionization energy. The more electrons that are stripped from the atom, the higher ionization energy you need for the next corresponding atom. So if I take an electron off an atom at a particular energy, the electrons are going to rearrange themselves where they may want to be closer to the nucleus, which means there's a higher attraction between the positive charge of the nucleus and the electron. So based off of that, you'll need more energy to pull the next one off, and then you'll even need more energy to pull the one off after that, and so on and so forth. So the ionization energies increases as you go up in the number of electrons that you want to remove, but it also increases in a particular way on the periodic table. So it increases in the following manner. As you read from left to right on the periodic table, the ionization increases. So noble gases have some of the highest ionization energies that there is because they're so inert, they don't want to give their electrons up because they require a lot of energy to take those away. So that's the reason why helium doesn't want to do anything. Now, is it possible? Yes, but you need a lot of energy to take the electrons away from those noble gases to do anything with them. And it also increases as you go from the bottom to the top. The reason being, for example, francium, since it has such a large atomic radius, the outermost electron is so far away from the nucleus that it doesn't even really feel that positive charge, which makes the electron so easily to be given away. So the ionization energy to take that electron away is very, very small. Same rules apply, but in general trends, the bigger the atom, the less ionization energy it needs to take that electron away. Electronegativity. Okay, so electronegativity is the tendency for an atom to attract a pair of bonding electrons. It's the tendency to which an atom wants to take electrons or want to bond with a particular atom of a particular electronegativity. Electronegativity is the key to detail how stable and unstable an atom can be. And the reason why is because, based off the electronegativity of an atom, depends on how much it wants those electrons. The way I kind of describe it is, which if you're a coffee addict or an energy drink addict, you always want energy drinks. You want to grab them as much as possible. I kind of describe that as electronegativity. So the more electronegative you are, the more you want electrons like all the time. Less electronegative, then the less likely you are to be an energy drink or coffee addict. That's kind of the best way I can think of. Sorry about that. All right. So A increases according to the following arrows as well. So A increases as you go from the bottom to the top of the periodic table, and A increases as you go from the left to the right. So it follows the same trend as ionization energy. And the thing is that the most electronegative elements are on the right-hand side because they want to keep their electrons, which means that it requires more ionization energy to pull those electrons away. So that does make sense. Francium, with being a higher atomic radius, it doesn't really care about its electrons, so it really doesn't want more. It wants to get rid of them. So that's the reason why it flows in the opposite direction. Electron affinity is the likelihood of an atom to gain an electron based on the energy needed to form a negative ion. This can get a little confusing because we just talked about electronegativity, and it's like, well, why isn't this electronegativity in regards to wanting to become a negative ion? Why is this electron affinity? I didn't make the term, but apparently that's how it is. So it's based on how easily an atom wants to become an anion instead of a cation. Again, something that's electronegativity and electron affinity are not the same thing. They are proportional to each other, and I'll show here in just a second why, but they are not the same thing. So they increase in a similar way as well. So electron affinity increases as you go from the bottom to the top of the periodic table, and then it also increases as you go from the left to the right. So electron affinity, you'll find that the elements that are more likely to form anions are on the right-hand side of the periodic table, while the elements that are more likely to form cations are on the left-hand side, which, if you know from the previous video, all the metals are pretty much on the left-hand side of the periodic table. So metals are more likely to form cations, while non-metals are more likely to form anions. And that's based off their electronegativity and what's called electron density. They want to keep their electrons so close to them, and they don't want to let them go. And since they have more electrons that they can take in and want to take in, they have a higher electron count compared to the positive charge, which makes them a negative ion. So that's the reason why that's that. So three of these trends you can actually correlate to each other. They follow the exact same trend, and they relate to each other in a certain way. They just have their own different definitions. So that's all there is for this video. Kind of a shorter video compared to the last one, which was like super long. But if you have any other questions in regards to periodic trends, please come talk to me, email me, whatever you need to do. Otherwise, I will plan on just seeing you in the next video and hope to see you in class. Bye.